Welcome back to topic 39 for Algebra 2, multiplying and dividing rational functions. In part 1, we're going to explore what is a rational function and how can we simplify rational expressions. So first, what is a rational function? Well, a function of the form f of x equals p of x divided by q of x, where q of x can't equal 0. Now notice here how we have p of x divided by q of x. So p of x and q of x, that's just equivalent to polynomials, but it's just writing it in a shorthand version. But because we're dealing with division, we're actually dealing with the quotient. So the quotient of two polynomials. You can also look to the title itself, rational function. In the word rational is ratio. When we deal with ratios, we're dealing with fractions. We're dealing with proportions. So, in this first example here, we have an example of a rational function, x squared divided by x squared minus 9. So, noted above, we know that our denominator can't equal 0. So specifically for this example, we know that x squared minus 9 can't equal 0. But can we become a little bit more specific? Because we have a variable here, x, do we have specific values that x can't equal? Well, if we look at x squared minus 9, we know that this is actually a difference of squares. So we can rewrite this as x plus 3 and x minus 3 can't equal 0. And using the zero product property, we know that this is the same thing as saying, well, x can't equal negative 3 and x can't equal positive 3. So because we're dealing with x and we have these restrictions on x, what can x equal? Well, because we're dealing with x, this is referring to the domain. So the domain, we know, is all of your values of x. The domain is all real numbers. Except when x is 3 or negative 3. So those are our two exceptions here, because if we were to plug those in, we would get 0 on our denominator, and we can't have our denominator be equivalent to 0. Specifically, when the denominator does equal 0, then the expression is undefined. And you all might remember back to when in Algebra 1, if we ever divided by 0, if we were graphing that, that is a slope of an undefined value. So undefined is just a vertical straight line whenever you have 0 in the denominator, but we don't want that here. So the domain of a rational expression is all real numbers except the values that make the denominator 0. So that's why in the example before, we had this restriction. We had the domain is all real numbers except 3 and negative 3, because if we plugged in 3 and negative 3, we would get 0 in our denominator. So in that first example, we couldn't simplify that rational function. But if we did want to simplify a rational function, we know that a rational function is simplified if its numerator and denominator have no common factors. Other than +1 and -1. So when simplifying rational functions, we're going to use this property, AC divided by BC. Now that's the same thing as A times C divided by B times C. And because we have C as a factor in our numerator and C as a factor in our denominator, they reduce. So all we're left with is A divided by B. So in order to simplify rational functions, you need to factor and cancel. So in this example here, it didn't really look like we factored anything, but we acknowledge that both C goes into AC and C also goes into BC. So we can call C a factor. And when we cancel, all we're really meaning is that it reduces to 1. So this is the same thing as times 1. It's just we normally don't write it once we get more comfortable with acknowledging that. So let's move on to our next examples. In example 1, we have 15 divided by 65. Now, if we were in middle school, how do we simplify this? We would think back to, okay, what number goes into both 15 and 65? Well, we know that 15 is the same thing as 3 times 5, and 65 is the same thing as 13 times 5. Since they both have 5 as a factor here, we can reduce. Now, a lot of people might just think, oh, you're dividing the numerator and denominator by 5. Exactly, that's what we're doing here. So this reduces to 3/13. For example 2, now we're dealing with variables. So we have 4x plus 12 divided by x squared minus 2x minus 15. We can factor the numerator to be 4 times x plus 3, because 4 goes into both 4x and 12. Our denominator, we have x squared minus 2x minus 15. So we need to think, what two numbers multiply together to get negative 15, but add to get negative 2? So especially with rational functions, you need to be very comfortable with factoring because it appears a lot. We can factor this to be x minus 5 times x plus 3. Notice how we have a common factor in the numerator and denominator. So we can reduce those. And all we're left with is 4 divided by x minus 5. But here we do have to mention those restrictions on the domain. So x could be all real numbers except when x equals positive 5 or negative 3. So we do have to take into account this value even though it already canceled out or it already reduced. Because what if we had a negative 3 here? This would end up giving us 0, and we would have 0 times x minus 5, which would result in 0. So we would have a product of 0 in the denominator. We want to avoid that, so we still have to identify that our domain could be all real numbers, except when x doesn't equal, except when x equals 5 or negative 3. We cannot have those values. Those values will be excluded. Moving on to example number 3, we have 4 minus x squared divided by x squared plus 3x minus 10. Now our numerator here has a difference of squares. It's just written a little bit differently than how we're used to seeing it because it has the constant first instead of the variable. So we can rewrite this still as 2 minus x times 2 plus x. Our denominator, we can factor x squared plus 3x minus 10 to be x minus 2 times x plus 5, because they multiply together to get negative 10, but add to get positive 3. Now here, I know your gut instinct is probably like, well, we can cancel out 2 minus x and x minus 2, because they look sort of similar, but they're not identical. We can, however, alter the numerator so that we can get an x minus 2. What we're going to do in the numerator is we're going to factor out a negative 1 out of this term right here. If we factor out a negative 1, then what we end up with is x minus 2. Because instead of x being negative like it originally was, it changes to positive. Instead of 2 being positive, it changes to negative. All by just factoring out a negative 1. Then we still have our 2 plus x. Now my numerator doesn't change here, because still if you were to multiply all these three values together, I would end up with 4 minus x squared. So my end product doesn't change. Then we can rewrite our numerator. We still have x minus 2 and x plus 5. So in the numerator, we have an x minus 2 here and an x minus 2 there. So when we reduce, we get negative 1, or just a negative, 2 plus x, which we can also just write as x plus 2. Because addition is commutative, you can flip it. All divided by x plus 5. Now restrictions here, x is all real numbers except where x equals positive 2 from this part of the denominator, or negative 5. Moving on to our final example for this part, we have x times x plus 1 minus x plus 1 divided by x plus 1. So a whole lot of x plus 1s. If we just focus on our numerator, we know that they both have x plus 1 as a factor, so we can factor it out. Let's go with blue. So if we factor out an x plus 1, what's going to be left? Well, we still have our x, and then we have minus. Now, with our second term here in the numerator, this is really times a negative 1. So we're going to be left with x minus 1 as the other factor, all over x plus 1. Now when we reduce, we notice we have an x plus 1 in the numerator and denominator. So we'll end up with just x minus 1, where x can't equal negative 1, because that was in our denominator. Oh my goodness. Denominator there. So that is our restriction on the domain. And that is part 1. Thank you for watching.